Good morning, everyone. I'm Terje, and today I will show you how to set up and run a response simulation in NX SOL 103 RS. And I will use an example from NX10 user guide, which is an automotive bracket. And you will learn how to set up and run SOL 103 RS and how to apply enforced motions and how to run a transient dynamic analysis where the input excitations are time depending, and also a frequency response analysis where the input excitations are based on frequencies or depending on frequencies. SOL 103 RS is a linear solver. You can't have nonlinear effects due to contacts, large displacements, or plasticity. It's simply because it's based on calculating the modal participation factors of the included modes representing aerodynamics. It's not a direct solver. So why run it? Well, first of all, it's easy to set up and run, and that's because all features are supported by the user interface, and it gives you accurate results if the model is linear. However, there are also other dynamic solvers in NX, and SOL 103 is only calculating the eigenfrequencies and the mode shapes, but you can also use SOL 103 RS to do forced response dynamics. And in addition, you have 108, 109, 111, and 112, which can calculate forced responses, where the loads are inputs depending on time or frequency. If we look at transient response analysis first, you have the direct solver, SOL 109, which is calculating the nodal displacements directly when you have loads at no time. And then you have the modal solution, and NX SOL 103 RS is one of them. In addition, you can choose 112. What you do then is to apply time depending loads. You do a modal transformation of the equation systems, and you calculate the modal participation factors as a function of time. And if you have two equations or two modes representing aerodynamics, you only have to calculate two independent amplification factors for each time step. So this is a really, really fast simulation. But of course, you linearize the model, so it can't handle nonlinearities, obviously. Then you have the frequency response type of analysis, where the loads are depending on input frequencies. You have the direct solver, where you can include nonlinear effect. Both the mass, damping, and stiffness matrix might change, and you calculate the nodal displacements directly as a function of input frequency. The modal solution is linearized in the same way, so you can't have nonlinear effects, and you calculate the modal participation factors here as well, but then as a function of frequency. And I will show you two analyses which are both based on modal solutions in SOL 103 RS. If you want to do really advanced stuff, you also have solver SOL 601 and SOL 701, which is really the Adena software. 601 is an implicit solver, and 701 is a direct solver. And I will also post a video where I can use the SOL 701 to run crash analysis, which are really high-end nonlinear stuff. So please stay tuned. Now we are going to look at SOL 103 RS and how to use it. Here is the automotive bracket, the CAD model. And now I will first mesh this part, and then I will apply a concentrated mass in the middle of the surface with the mass of 0.5 kilos. And let's assume that this one is representing a device bolted to this bracket. Then I want to fix this top surface in all directions except for the vertical direction, because I want to apply enforced displacement on the nodes on this top edge. And then I will do a calculation of the modes, modal analysis, and then I will use a certain criteria to identify those modes that contributes most to the vertical displacement of this additional mass. And remember that 103 RS is not a direct solver. It uses those selected modes in order to calculate the dynamics. And what NX is doing then is to calculate the modal amplitudes or participation factors for each mode involved in the simulation. So let's do the meshing first. We go to Application, Pre and Post. We create a new FEM and simulation. And we don't need an idealized part file. And we choose SOL 103 Response Dynamics. And initially we can keep all the default settings. So then go to the FEM file. And first I want to apply a mesh point, because I want to put an additional mass in the center of the surface. So that means I can use the surface coordinate 0.5, 0.5. There we are. Then we can mesh this structure. We use 4 element thickness, sequad 4 elements. Okay. And we can see that since we used a mesh point, the mesh has adapted, and you will have a node in the center here. And there I want to apply a 0D mesh. I want a concentrated mass, and I apply it here on the mesh point. And then I want to define the properties. I want a payload or lumped mass of 0.5 kilos. So there we are. Then the finite element model is ready. No, it's not, because we of course have to define the shell properties. First of all, we need to make sure that we are using a steel property. We could use inherit, because I think the geometry has been assigned steel materials. But we need to define the thickness, which is 1.5 millimeter. So there we are. Let's have a look at the simulation file. First, I want to apply some boundary conditions. And I start with user-defined constraints on this surface. And here I want to fix all degrees of freedom except set, because I want to apply enforced displacement of the top edge in that direction. So we can call it free set. There we are. And then I need an additional constraint, and that will be enforced motion location. And then I use feature edge nodes as a selection filter, and I click on the top surface there, and NX automatically selected 11 nodes here. And on these nodes we want to apply an enforced motion in the set direction. And this enforced motion could be a displacement, velocity, or acceleration. So there we are. And now we are ready to run. I forgot one thing. I have to change the output requests for this simulation. And I have to select acceleration, modal effective mass, and modal contribution. Those two last print options here allow me to select those modes which contribute most to the vertical displacement of this additional mass. And I will show you how. And let's make sure that it's the right output request. Okay. Then we can run the solution, which is very fast. There it's finished. And what I've done now is to actually calculate the component modes and the constraint modes that my model gives me. And here you can see the first flexible mode. It has a frequency of 34 hertz. The next one, 172. And the third one, 341. And then it's a big step up to 640, which is the fourth mode. But if you step back, we can see that this mode, you can tell it slightly contributes to this set displacement of the structure. doesn't move the additional mass much, but it moves the other distributed mass in the shell elements a bit, not too much. Let's check the second mode. Well, it doesn't contribute much to the set deformation of the structure, a little bit perhaps, but then this one, it contributes a lot to the vertical displacement of the additional mass and also the shell elements. So just by visualizing these modes, we can tell that the first and the third mode is probably the most important modes in order to simulate the dynamic behavior when we apply a vertical enforced displacement. Although the second mode have an influence, we will check it later. Then we need the constraint modes, and let's have a look at those. They are only unit displacements in the enforced degrees of freedom for each node on the top edge here. So we have actually not yet applied any kind of enforced motion or force to this structure, so we can't say anything about the amplitudes or the dynamic performance. But we know that mode number 1 and 3 is probably those modes which contribute to the dynamics most in the set direction. Then we are going to use the component modes and the constraint modes in our new simulation sequence, which we will create. We create a new solution process of type response dynamics. Accept the default settings. And here you see we have response dynamics 1, and here we get access to the normal modes and the constraint modes that we just calculated. Let's have a look at the normal modes. Here you see the frequency of the modes and both the undamped and the damped frequency. First, we are going to apply some damping on these modes, and then we can right click on normal modes and we do edit damping factor, and let's apply 4% damping. Okay. Then we have 4% viscous damping, and you see that the damped frequency has been reduced with a certain factor compared to the undamped frequency. And this factor is the square root of 1 minus the damping ratio in the power of 2. What you also see here is the modal participation factors in X, Y, and Z direction. And we are interested in the Z direction, because we're going to apply an enforced motion in this edge in the Z direction, and then we want to check out the response for nodes on this lower bracket, part of the bracket. And what we see here is that mode number 1 actually contributes to 93 roughly % of the mass motion in that direction. And then we can neglect mode number 2, but mode number 3 is of interest. It contributes to 2% of the mass motion. And then there are no other modes interesting, except for mode number 7 perhaps, but it has a resonance frequency of 1947. And that's far beyond the excitation range that we will use in our simulations. So we have applied damping, and the next thing we'll do is to deactivate the modes that we don't want to care about. 4, 5, 6, 7, 8, 9, 10. We right click and deactivate. So what have we done now? Well, based on the modal participation factors, we have selected the two modes that contribute to roughly 95% of the mass motion in the Z direction. And a general rule tells me that if you have a total mass contribution of 80% or more, you get quite accurate results. In this case, we lose like 5% accuracy compared to if we did run a direct dynamic simulation and calculated the nodal displacement for each time or frequency step. So that means that we are actually reducing the equations from 2000 coupled equations in a direct solution to a system of 2 uncoupled equations based on the modal solution. And now, when we will run the various transient and harmonic loads, we know that we can predict the response for each time or frequency step efficiently by using calculating only 2 modal amplitudes And that's a great achievement without losing much accuracy. So let's start applying loads. First, I will set them and run a transient dynamic simulation based on the two modes I've selected, those two activated modes. And I want to apply an input acceleration in the middle here on the top edge, and I want to measure the response in the additional mass point here. And the first thing I do is to go to response dynamics, and then I create a new event. I can call it event half sine. And then I use data recovery method, modal displacement, user defined. My duration time is 0.5 seconds. And remember, this is a transient simulation, and then I apply displacements, forces, etc. as a function of time. The initial conditions are 0. That means the modal amplitude or the deformations are 0 initially. Then I'm ready to apply an excitation. And then I must first make sure that I have a function available. And I don't have the Java runtime library available on this computer, so I have to use a function which I've already created. It's I go to associated AFUs and I open, and I select half sine pulse AFU. Okay. Then I want to plot this one to make sure it's the right one. Here it is. And let's just edit the function a bit. Let's change the range to from 0 to 1 to make sure it starts and ends as it should. Okay, this looks good. This is the function I want to use. So then I go back to my excitations and I create a new excitation, translational nodal. And I call my excitation half sine. And enforced motion is okay. And then I use the list. And I think my node in the middle here is 329. So I choose that one as my excitation node. And you know that in this node I have only one free degree of freedom, which is in the Z direction, or it's actually an enforced degree of freedom. So now I pick up my function here. Is that one? But as you remember, the amplitude was 1. And I want to apply something like 5G, which is probably the most severe vertical acceleration on a car. That's common practice, I think. And when I give this acceleration in millimeters per second in the power of 2, I need to use 49,000. And then I press apply. And then I have my event, I have my loads, and I have my constraint modes and component modes, and I can run the simulation. And I want to calculate the modal response for these nodes I'm selecting. Then I use acceleration, response node. I choose this one, where I have my additional mass. And then I want to check the response in the Z direction. I could store this in an AFU function. I think I'm fine. And then I press apply. And here is my transient response. You see that the peak acceleration in this bracket is 94,000 millimeter per second in the power of 2. And the excitation peak was 50,000. So I have an amplification factor here. And due to the viscous damping I applied, you can see it damps out nicely. And if you check out one of my other videos, I show you how you can calculate the logarithmic decrement and the damping ratio based on measurements. So this was the first transient simulation, and you can do a lot of other simulations as well with other type of inputs, so please experiment. Then I want to run a frequency response simulation. That means that the input excitations are a function of the frequencies. It's not a transient simulation anymore. The easiest one is probably a transmissibility study. And transmissibility is a type of FRF, frequency response function, that lets you evaluate the response of one or several output nodes to an enforced motion, such as displacements, velocity, or accelerations at a selected node. And a common application is to study how wheel excitations and engine vibrations are transferred to the vehicle body. In this example, I want to apply an excitation in this center node here, frequency dependent, and I will watch the response of 1, 2, 3 nodes on my bracket as a function of input frequency. And I call this node 1, and this node 2, and this node 3. And the first thing I do then is to go to evaluate transmissibility. The results are accelerations, the inputs as well, and I want to choose my node number 329, which is on the middle of this edge. That's my input, and I want to study the response in the z direction. And I use a frequency range, and I start at a frequency of 0 Hertz, and then I increase gradually the frequency to 400, and I do it in 400 steps. And then I can check, well, first I have to select the nodes, obviously. I select this one, which is the inner node, and the node where I have my lumped mass, and the outer node, node 1, 2, and 3. And then I can run the simulation. And as I said, this is just the model is represented by 2 independent or decoupled equations, so it's extremely fast to run. And here is the response already. What you see here is that the blue line is representing the inner node, the red line is representing my node where I have my additional mass, and the green line is representing my outer node, node number 3. And you can see that in this frequency range, where I have my first resonance frequency, 34 Hertz, I have an amplification factor of almost 3 on the outer edge, the node number 3. And in the middle, where I have my additional mass, I have an amplification factor of roughly 1.2. And then we can see that the inner node is not influenced by any kind of resonances. At least not resonance frequency 1 or mode number 1. If we go to the other end here, we see that at roughly 340 Hertz, we have mode number 3 and eigenfrequency number 3. And we see here that the only node which is influenced by this mode is node number 3, which is on the tip of my bracket. It has an amplification of roughly 1.5. So as you can see, this is the transmissibility study is a very nice tool in order to check how vibrations are transmitted through your design. And then you could select which nodes you think are of interest, and those nodes are probably nodes where you have some kind of delicate instruments. And the input nodes are where you have the load from excitations, obviously. In this example, you should probably check out if any other nodes in this frequency range influence, because like node number 3, it was on the corner node of the bracket, and it might be that mode number 2 should have been included in this simulation. Please try.